on behalf of Space Education and Research Foundation, and on my personal behalf, I welcome the speaker for this webinar, Dr. Megha U. Bhatt, and all the participants from different countries who are taking part in this webinar. And this is the last and the final talk of this webinar on remote sensing of planets. So any doubt that the participants have on today's presentation or in the past three presentations that Dr. Megha Bhatt has given, you can ask questions regarding all of them, and she will address those questions at the end of her presentation today. And before I hand over the mic to Dr. Megha Bhatt, I will say a few words about her. Dr. Megha Bhatt is a scientist in Planetary Science Division of Physical Research Laboratory at Ahmedabad, which is a unit of Department of Space. And she has done extremely good work on the exploration of solar system. Mainly her work, most of her work is related to research on moon using the spectroscopic observations. With these few words, I now request Dr. Megha Bhatt to start her talk. Dr. Megha Bhatt, please.
Yeah, thank you, Dr. Hariom Vats, for this introduction, and it's like thank you very much for this opportunity. This is the fourth and the last webinar of the series, and the title of this is Advances in Planetary Sciences. So in the last three webinars, we have kind of a broad overview about our solar system, inner planetary bodies, and then some of the tools like reflectance spectroscopy, and then specific concentration on remote sensing of moon. So those were like, and the level of the talk I have kept very basic so that everyone can follow. And it was a very nice interactive session last time. And just based on that, this is the last talk of the series where I am like, because we are now familiar with the inner planetary bodies, we are familiar with kind of missions we have, and we are familiar with kind of tools we can use. So with that, what we can do next? So we have to prepare our younger generation for the next decade of exploration. So what do we expect? What we have like learned in last decade or like ongoing time, and then what else actually we can, or how we can actually improve on that. So I will just take few examples just to give you glimpse of that. And obviously, like whenever you have a certain question, you can always come back and ask. So just to summarize in a very brief, that in the last few, let's say 50 years of exploration, we have learned a lot about our overall solar system. So we have started from having point observation, and from that now we have maps, very detailed maps of our different planetary bodies. So that actually helps us to understand so every individual planetary body, the understanding of every individual planetary body actually helps us to understand the overall evolution process of solar system. So how the system was formed, which are the main dominating processes. So all this actually, and to get the overall picture of our solar system, or the how actually why Earth is unique, basically to understand why Earth is so unique, we have to actually explore each and every planetary body. So, and in the last 50 years, actually, we had missions, orbiters, landers, rovers, flybys to most of the planetary bodies, including inner and outer planetary bodies. So with that, actually, I have just summarized few few points here, that before Apollo missions, or before actually, let's say 19 up to 1990s, our understanding was that moon is actually born dry. But then, with new enhanced technologies and with new tools, actually, we now have a very good understanding, and we are very much convinced that uh, we have the deposits of water ice is present at the moon's poles, and that has actually changed our overall perspective of looking to moon. And also it has, I mean, the understanding what we are actually uh, getting in case of moon is actually very very important to have the overall picture of the solar system. Then before, there was, though some assumptions and some understanding, but now we with very confidence, with all rover missions and lander missions and orbiter missions to Mars, we know that Mars had early warm and wet climate, suggesting possibilities of life. So this is another very important point what we have now understood in last couple of decades. Then Venus may be volcanically active. So Venus is a body. We actually do not have too much information. I mean, we know that it's a one plate body, and it has it has resurfacing events in past. So but was it like at any particular time it was possible to have running water in on surface of Venus? That is what we are still trying to explore, and with our new future missions, and even India is planning to have future missions, and with that actually we are still further, we want to have in-depth knowledge of current scenario, which can be actually put again in the inverse modelings, and can actually give us information on that what would we expect in the past, or what would we expect in the future, long future. Then Mercury, which was always thought that because of the very nearby location to Sun, there is no chance to have ice deposits. But what turned out with a messenger mission is that actually Mercury's pole also contains thick ice deposits, and some estimations actually suggest that the content of ice deposit is actually much more in comparison to moon. So this is also a very I would say it's a very important discovery what has come in last few decades. And then if we do in this webinar, we have not touched to giant bodies and its satellites, but it's worth mentioning here that actually there are several of though like these are gas giants, but still if you look to moons of this gas giants, actually they have like many, like in the first webinar we talked about all these things, that actually Saturn and Jupiter contributes, I mean they dominate the overall satellite system of our solar system. So we have now evidences of liquid methane rain that falls on Saturn's moon Titan, and that actually creates rivers, lakes, and landscapes very similar to Earth, but obviously with the main composition, instead of water it is actually methane. But if you compare the landscape, it's actually has similarity with Earth. So obviously it's worth again exploring Saturn's rings, because it has a huge ring system, which is actually and all the satellites rotating around Saturn also get affected or get influenced by the Saturn's gravity and its ring system, that provide us a very good opportunity to understand the nature of planetary accretion in the very beginning of our solar system formation. Then we have also observed plumes of ice and vapors from Enceladus, again satellite of Saturn. Then Jupiter's satellite Europa. Probably, I mean, it has, now we know that there are evidences, and its ocean might support actually life. So we do not have any kind of that, I mean, we have to again in the next round of exploration we have to go, because these are the planetary bodies or the system which actually it's not too far. So because the ultimate aim is to find earth I mean, we have to find that if life exists somewhere else, and to start with that, actually, the first thing is to have like as to explore options which are actually not too far. So if we consider exploring other solar system, we should at least have a very good understanding about all unique family members of our own solar system. So Europa is another very interesting body which we have to explore in detail. And then the impacts on Jupiter, we have now observed that that produce Earth-size scar in the planet atmosphere, and it's the atmosphere dynamics is a very important thing to understand. So and all this is possible because I have just given one example of a topographic data, that how it actually help us to enhance, like we keep uh, increasing our spatial domain. So we are like from kilometers, hundred of kilometers, to we have now narrowed down to few hundred of meters, and that is because of the all sophisticated technologies, tools available to us. So before, like we the obviously, as you know, that the satellite mass is actually is very limited because of the our launching I mean, it's directly related to our launching capabilities. But as the overall mass of each individual payload is decreasing day by day because of the advanced technologies, there is more and more room to put more number of instruments, and with a specific scientific objective on a specific mission. So just as an example, that you can see that this topographic data, before we did not have it in that detail, but now we have it for at least for all inner planetary bodies that actually provide key information for distinction and geologic interpretation of surface features by using several independent techniques. So we do not rely on a specific thing, like there are instruments to measure topography, some dedicated instruments like radar and laser altimeters. Whereas if you do not have that kind of instrument on board, yeah, still if you have a very high resolution stereo camera, or even if not a stereo camera, but if you have repetitive observation that you can actually use to generate very detailed topographic maps, and that actually provide and that's obviously from and then if you have several missions, actually you can even try to merge information from several missions. So basically the topographic information support the geologic interpretation of surface features, which is very important. If you do not have understanding of topography, it becomes very difficult to actually interpret the results for related to morphology or any specific surface feature. So just as an example, what I have shown here is just like a very recent work what we did for Chandrayaan 2 landing site. We actually counted craters, and then what we saw is that there are some very obvious fresh craters, and there are some degraded craters, some old craters, and but as like if you can see this one, actually it's very difficult to say that it is a crater. So it's called as ghost crater, and this can only be identified by topographic profile. So here you can see the topography profile, that wherever there is a crater, there is a depression, and that actually you see for this and this crater, this one belong to this, which is like in the image is actually we can't make it out that it's a crater, but there is a depression. So if we land here somewhere, though on the on through the uh, pictures, we will not find that there is a dangerous crater sitting here, but because of its topography, detailed topographic maps what we have, we know that this kind of places we should actually avoid. So in landing site selection, visibility between instrument and earth and the absence of high slopes and strong surface roughness is very important constraint, and specifically this high slope we can actually avoid by considering a very good, very high resolution topographic data. So this is how we have actually advanced in the last decade, and now we have a very good confidence about like that. Even before landing, we can actually assess that area in a very detailed using the topographic and its photometric information and several other information. So basically one has to actually combine information from different sources and get the overall information. Just as a second example of topographic data, actually what we have is topographic map of Venus. So we actually did not know about a global topography of Venus until unless this mission in 1990s that actually provided us first global maps or topographic maps. And what we can see is that this bluish colors are actually plain areas, and whereas this red colors, the bright colors, are actually very topographically high areas or very bright areas, and there are some rifts also. So all this actually, because direct imaging of Venus because of its cloud is not possible, but through radars actually we can get topographic information. And what we see is that very topographic variations on Venus are deeply compensated through upwelling and downwelling processes within the mantle. So though there is no plate tectonics, so you do not see that kind of horizontal movements, but what we can see actually in case of Venus is that there is actually vertical movement, and that actually give rise to this kind of topographic features. So until unless we do not have this kind of global maps, actually it's very difficult to have to develop our understanding about the evolution of the of a specific planetary body. So just as another example how we are actually improving day by day, what you can see is that this is a Clementine image of Tycho crater, and I have just plotted one of the instrument on Chandrayaan 1, SER2. So these are the tracks of this SER2 instrument, and because this is a point spectrometer, we have to actually plot it on image to get its information like topography information or overall like context of the like where exactly we are looking to that. And if you zoom to this image, what the best we could have up to that time was a picture like this, but that substantially improved with the next generation of spacecraft. So what you can see is here, just this particular part I have now plotted here, and even and in the Selene mission images very clearly actually we can actually put SER2 footprints on this central peak. And even one step advance is actually LRO images, or the narrow angle camera images, where I'm just showing you as an example. This is a only one footprint of SER2, which actually tells you that the area looked by the spectrometer is something like this. So you can see that how actually we can go in a very finer scale, and it's like just like get you are getting images from very high resolution camera, use like just you use your own camera to get a picture of your surrounding. It's that kind of scale what we are now looking, so that actually helps us a lot to understand. And then what you can see is that within one footprint of a of this instrument there are variations. So whatever the signal what we are getting is actually is a combined signal what we get from this. So we can't distinguish between different uh, lithologies or different. I mean, within footprint, whatever you are having is actually a combination of, and that is actually explained through this example. Another example, if we take, and I think I have shown this to you before also, that how we have improved in spectroscopic measurements. So what we had before was in terms of few filters from Clementine or even from Saline mission. It had a multispectral imager. So we had few filters, and then you have to actually uh, fit line to that to actually get the absorption features. But from that time to now, actually what you can see is that we have a very good finer spectral resolution as well as spatial resolution, and that actually helps us. Like here what I have done is I have actually grouped the similar kind of spectra, and that actually start telling us a story. So this much of enhancement in our understanding we have made in last few decades. So that actually with all these advanced tools and technologies, now we have ability to actually look in much more detail to our inner planetary bodies as well as our outer bodies, or the satellites of Saturn and Jupiter, which has potential to hold ocean beneath, and at least it gives us opportunity to study another kind of environment, which probably has linked to the overall. I mean, it obviously helps us to understand the overall solar system evolution processes. So, just so basically, this is I have titled it as roadmap towards in-depth understanding. So how we should plan. So basically, we should define our scientific objectives, what exactly we want to do, then identify the measurements critical to answer those questions. So suppose, for example, if you consider this MAVEN mission to Mars, that actually the main objective of MAVEN mission was to understand its Mars atmosphere and the atmosphere surface interaction processes. So they carried instrument in that particular line. So they do not concentrate on having a very good resolution, high resolution imaging kind of instruments, but their main idea was to actually carry the instrument which can actually do atmosphere profiling. So then we should have an exhausted list of instruments that is capable of doing those kind of measurements, and identify area where the scientifically desired measurements are not feasible using available instrument, because there is always a kind of mismatch between like what we as scientists want and what in form of technology is available with engineers. So there is a that kind of synergy is very much important to establish between engineers and scientists. So you have some specific scientific goal and you want to achieve that, and for that you need a certain kind of measurements. Now that kind of measurements, what kind of instrument actually can do that kind of measurement? So that is very important to actually critically look and examine that what is the feasibility basically. So here just as an example, I have taken this Chandrayaan 1. So the main objective of this mission was to enhance our understanding of having mineralogical maps and the geochemical understanding, or the how the basically to understand how the moon was formed, and how it the processes which actually modified the surface. So for that, as you can see here, that we had a complete suite of instruments. This is like covering spectrometers, having this kind of X-ray spectrometers, which can actually directly give you elemental abundance. This mineralogical analysis can be done using this kind of near-infrared spectrometers. Then we had this moon impact probe, and then we had this SENA and SWIM to actually look to the exosphere, or the basically the high energy particle population. Then we had this TMC, which actually provide us very high resolution images in a stereographic mode, so that we can have topographic, very detailed topographic information. Mini SAR, which can actually tell us if ice deposits are present on poles or not. So this was like a this is an example of having instrument in a all kind of wavelength range to get a overall broad picture, or the kind of a broad understanding of a planetary body. But when you go with a specific goal, as we already discussed this Maven mission, then you actually concentrate on having only those kind of instruments. So that really depends on what kind of what is the objective of sending a spacecraft. So here just I have listed this five different missions, almost from the same decade, and with its objective and its payload. So there are many overlapping also in between, because many of them actually had the science objective also actually overlaps, and that's why you see many overlapping in the instrumentation. So now for the next kind of generation of exploration, the main interest is to hunt for organics, because we want to know that how basically, or is it possible to have life in any form, in not maybe in the form what we are seeing on Earth, but is there possible to have some kind of some form of life which and then if you want to hunt for that, what kind of areas you should look. So basically scientists have identified that there are three necessary criteria for life, and that is a fluid medium, so basically in our case is water, a source of energy, and then uh, constituents and conditions compatible with polymetric chemistry. So there should be a way where you can actually, the molecules can simple form of molecules can actually combine and can form complicated form, which we can then say that it's a way of actually finding organics. So have we found organic molecules in space in our own solar system? Yes, I'm just showing you two examples here, and this is Io, and this is Europa. And what we know from Io is that it has more than 400 active volcanoes, and these are powered by tidal heating due to its orbital resonance with Europa. But the main source which actually modifies the surface is actually sulfur, and that actually is present in form of all allotropes and compounds that is released from plumes and lava flows. This is a case. Probably right now the situation is like this, but if we do inverse modeling, just if considering that this is the present scenario, what we actually know from modeling result is that at some point in the past, probably Io was water rich, and with averaging temperature of minus 25 degrees centigrade, and rather than having this 2000 degrees centigrade of lava spilling right now what we have, and on the surface of 113 degree centigrade. So basically the situation, I mean, once you know the situation, present situation, actually you can model what would be the case in the past, and that actually makes this IO. And for next session of next level of exploration, it makes it as a very interesting body. Another thing is, like, we take Europa, or like Ganymede, Europa, and Enceladus. All three satellites actually have hot iron rich cores surrounded by a thick water mantle and an outer crust of water, ice, clay, and organics. And in case of some of these bodies, we have actually seen plumes releasing this kind of organics. So we have evidences for that, and actually that is why it becomes very important to study these bodies in detail. Though we have not done it so far, we have few flyby missions, but we need dedicated missions to actually study these bodies in much more detail. Orbiter missions as well as lander missions. Just as an example, very interestingly, if you see this Rosetta spacecraft, which landed on Comet 767P, that also from lander, not from orbiter, from lander, it actually detected organic molecules. So even it's possible to detect. I mean, that's why, like, it's important to have lander missions, because that gives us much more better hold on understanding. Obviously orbiters are required to have a global perspective, and but then we have to narrow down and go to a specific areas to actually look in detail, like the kind of in situ sample analysis. If we look to the near future, there are plenty of missions like ExoMars, Hope, Mars 2020, Osiris, Hayabusa 2, Chang 5. So these are some of the missions which I have just listed here from this particular source. Maybe some of them are active, maybe some of them are called off. But what I want to say with this slide is that there are many more specific missions. So now, as like we have now a global kind of understanding, and now we actually really want to go to a specific. We have to explore the bodies with a very specific scientific objectives, and these are the missions which are having that kind of specific scientific objective to explore a specific planetary body, which is going to again enhance our knowledge, which will be definitely will actually help us to get the overall understanding of our solar system evolution processes. Now if I narrow down and go back to our nearest neighbor, this our moon was actually initially thought of as having no I mean, it was thought that water do not play any role in the formation of moon, but that has been now challenged with the new results. And what we know is actually that there are evidences. So we have reanalyzed Apollo samples using new techniques and new instruments, and what we know is that there is a possibility to have endogenic water sources. We from orbiters also we know now that there is kind of I mean, it's more on poles, but actually the picture has been now changed, and actually you even can have water signature or the volatile signatures on equatorial regions, or almost globally you can actually map that. So that has again changed our views. And before we had the understanding that moon was formed through giant impact, and but this hypothesis is again challenged with this new sets of results, because now we have to include role of water in the formation of moon, and also subsequently formation of earth. So the new results are actually bringing up new challenges, which actually again need new missions to address. Another source what we see in polar regions, and that is the this is actually, this map is derived using Chandrayaan 1 mini-SAR data, where we actually see enhanced polarized signature, which is actually, which tells us that this surface is rough and probably actually accumulates ice. And by combining some of this diviner and low-lying M cube data, now we have actually identified exposures of ice for north and south pole. So this has greatly changed our overall thinking, or our overall understanding of earth moon planetary system. So if we just summarize that, there are now different ways what we know, that there is like solar wind related hydrogen what we get in the first few centimeters of regolith, but there is also a source which is coming from deep, and that also actually contributes. And then there are meteorites which actually which actually brings water to the surface. So with this understanding, what we can say for sure, with modeling efforts, so observations and plus modeling, what we know is that the moon is particularly the moon and the particularly the permanently shadowed regions are most probably has a net water loss regime. So this is like to basically moon is losing its water, and to sustain this loss rate over geologic time, the water must have been delivered long ago, or it was present at the lunar formation. So this kind of modeling efforts actually tells us that actually right now moon is actually in the phase it's losing its volatiles and its water. And if we have, even now if we can actually detect it, so the source should be actually from the time which was delivered in the very long ago in the past, or maybe from the time of its formation. And and then what we know is that there is a layer of regolith which has uniformly hydrated soil, and which is covered by the again topmost layer, where you can see that process, I mean, if impact happens which can actually remove this first layer, then this layer is again exposed, and that again actually actually release water in exosphere. So basically, one has to understand the surface exosphere interaction processes. And the PSRs, because it has higher water concentration compared to average lunar soil, it has suffer a much higher net loss from meteorite impact. So if a meteorite impact happens on equatorial origin or in a PSR, the rate of loss will be actually higher in case of PSI in comparison to equatorial region. So that this is a kind of a overall understanding what we have achieved in last few years, and that is actually this is a kind of a building block for us for the next generation of exploration what we are actually for which we already have a roadmap ready. So another interesting result what we now know, I mean, and I'm just showing you results from last 2 years. So I'm really keeping it like only the recent work what I'm trying to show you. Now we know that, and this is again a modeling work, we know that impact material is actually like if there is an oblique impact, the possibility or the probability of holding this material on surface is actually very low. So and then if the angle is higher, then it can actually penetrate in deep and can actually sit in the surface. So the fraction of impactor mass that could be retained by planetary bodies have been examined using and for this actually they have used millions of computational impact simulations. So they have to see like at what time what kind of, and this has implication to all inner planetary bodies because the flux of impact is kind of same for the all in, inner solar system. So we consider that Earth, Moon, Mars, and Mercury, Venus actually had the same flux. So the results what we derive for Moon actually is actually also implicable to Mars. So, and then the material from large impactor is less effectively retained than that from smaller counterparts, and that higher angle impacts delivered a large mass fraction to the body than do low angle impacts. So that's the thing that if there is a low impact and obviously the escape velocity is higher, the chances are of having of losing the material is high. But in this kind of impact, it can actually penetrate in deep and can actually retrain there for a longer time. uh, then another study, if we consider again, this is based on observation as well as modeling. So what this team has found is that the thick ice deposits in shallow simple craters on the Moon and Mercury. So they are talking about that because in case of Mercury, it is observed through messenger data set that there are like thick ice deposits mainly in shallow simple craters, whereas in case of Moon we have seen that the amount of ice deposit what is estimated is much lower in comparison to Mercury poles. So therefore this kind of simulation study and along with modeling work, they have combined it with observations. So these results are actually based on, so they have concluded that there is a relationship between depth and diameter. And what happens is when a crater forms and then a layer of ice is deposited on that, and then again because of the nearby impacts the material is ejected and again put it on this particular crater. So you see ice in form of layers, and this result is actually based on this depth and diameter ratio of approximately 2000 simple craters from Mercury North Pole and from 12,000 lunar craters from moon. So the results which are derived from Mercury are kind of applied to moon to see that if same kind of ratio exists in case of moon or not. So this actually gives us a kind of a map where actually we can say that okay, these are the specific areas where we have maximum possibility to have thick ice deposits, and obviously those will be the targets of next generation lander and rover missions. So this is because the volatiles and water is kind of a main objective of exploration for now. But there are many other, I mean, to develop the overall understanding, we actually have to combine results of the expertise from different regions. Just hello, just I call you back. So sorry. So basically, as one of the application, what I'm showing you here is actually we have now very detailed maps where we actually can tell that like this is the map which actually tells us that volcanic features on moon. So there are volcanic domes, there are floor fracture craters, pyroclastic deposits, and impact basins. So obviously when you start mapping things, you start getting the correlation. Why specific I mean why we have, is there any correlation between basins and floor fracture craters or the volcanic domes, and basically why and how we get this kind of features. So on the surface, so that actually greatly enhance our understanding, and this kind of detailed maps are possible now because we have many years of global data sets which can be again merged and combined to get to give us a very detailed information. So another thing, another example here is this magnesium-rich spinel. This was actually found from Chandrayaan-1 mission near around Mare Moscovici basin. That some of this spinel exposures are there, which was actually not expected to be identified using orbiter missions. But then later, these exposures have been mapped. I don't know, around about 22 locations have been around that is have been identified, which actually shows this exposure. And now with by combining this information with topographic details, like this is a topographic map, or with crustal thickness map, when we put the same locations to crustal thickness map, what we see is that it has some kind of relation. So what we can see is that mostly this mg spinel rich lithology is found around basins, or the or in some specific small craters which are actually is related to thin crust. So basically what we can say is that the origin of this magnesium spinel is actually from the crust, or the deep layer of the crust, because the crust, or maybe the first layer of the mantle. So all this we can say based on if when we combine the observations from different data, observations from different I mean, if we combine this topography, crystal thickness, and then spectroscopic observation, then we get the overall picture. So this kind of understanding we have developed in as mainly in case of moon, because we have a very long period of observation, and with and we have now many global observations of moon through orbiter and through telescope, the near side of the moon. So with all this, actually now we can prepare detailed global petrologic maps of moon, which can actually, so here this blue color it tells us that this is actually highland kind of rock, and then within Mare also we can see differences in color, which actually tells us that is it like in a very simple term, is it magnesium rich rocks, or is it iron rich rocks? So that kind of different compositionally different units actually we can map, and then we can actually try to infer that it's if this specific kind of rock is present. I mean, when you, this is a kind of global map, then but then you can go to site specific study, and then you can actually look like this is a Mare Moscoviensis. So within this area you can actually look that what are the variations you are observing, and then what kind of processes probably worked to get this kind of variations on surface. So that actually again enhance our understanding on interior processes, because this surface is the only way or how we can actually explore interior of the planet, because we whatever we observe is actually mainly from the surface. Another example is that not only that we have global volatile or hydroxyl maps, but what we can see is actually there is variability from morning to evening. If we divide our data, because we have now data for continuously for a year or so, and with now our Chandrayaan 2 mission, we hope that we will have a very good database for very consistent database for a longer period of time. Then what we see is that actually we can actually divide data into morning, midday, and evening slots, and then we can see the variation. And just with this superficial water signature or the hydroxyl signature, what we can see is that there is variation. So this is the same side of moon what is shown here. This is Mare region and this is Highland region. It's like uh, this is Orientale basin, and what you can see is that there is variation. So this is the IBD, this is integrated band depth. So this is taken for 2.7, around 2.7 micrometer absorption band of M cube. And what we can see is that in morning it is more than in the afternoon, or in the midday it reduces, and then again in evening it starts accumulating. So this kind of time of day dependent behavior of hydroxyl or H2O was actually not known before, but with our Chandrayaan 1 data we could actually do all these things. So that's why like we and then now we have understanding, okay, this kind of variation actually happens in case of moon. Another example, if we take, we have now resource maps. So like helium is the main resource what we look for, and this kind of global maps can be prepared based on our understanding on sample analysis, and based on the looking to some kind of correlation between some specific element what we can measure remotely, and then to have it. So what we have seen in case of uh, moon, that this helium 3 is, I mean, from sample analysis we know that it has relation with titanium. So because titanium is something what we can actually estimate using orbiters, we can actually prepare global helium maps which can actually help us. Suppose if one want to like specifically this Korean mission, their main concentration is to look for landing site which is helium rich, to actually land there, and to analyze and to get more understanding on the resources. So this kind of stuff can be done and can be bring out to one level advance with new and with new missions, new plant missions. Another thing what we can do with this kind of global data sets is kind of a classification. And this was a very kind of a, this is a preliminary work what we have done with students here, is like we just used a machine learning approach to see that if we, because we have now a very good data, very huge amount of data, can we train our system to look for a specific kind of variation? And what we can see is that in the first order it can actually distinguish between different Mare units, and even it can pick some differences in highland. Obviously, this kind of methodology has to be refined further, but this is just to give you a flavor that with having like more and more advanced tools available to us, that can also be used to dig the data and try to get more and more information. As we have good understanding of space weathering effects, how the space weathering is actually affecting the surface. Because we have that information now, with some kind of modeling, like in this paper, they have done this radiative transfer modeling, and that they have again verified on Apollo samples, because in case of moon we get good confidence because we have return samples. So based on that modeling approach, now we have space weathering maps. It's the first time we have this kind of space weathering maps. We had OMET kind of maps from the Clementine mission, but this is a kind of a new maps where you can see that the fresh craters are showing less amount of nanophase iron, whereas the old surface like this highland area, some of this areas which actually shows more amount of nanophase iron. And not only nanophase iron, actually they could actually come up with a way of distinguishing between nanophase and microphase iron abundances. And what you can see is that this microphase iron abundance is not exactly related to this nanophase iron. So that both the things actually give us independent information, which is very important. For example, if we do swirl studies, then we have to obviously the nanophase iron production is less there, but the microphase iron production is same. So this kind of maps are also very important for that kind of site specific work. And another thing, what like I'm a part of that work, is we have now first time the global elemental maps of a very high resolution derived from Chandrayaan-1 data. So here you can see this iron, iron and calcium and magnesium, and the overall variation, actually the global variation we can see. Obviously, this kind of indirect way of developing tools or developing methods have its own limitations, but obviously with the new missions and with the new tools, we will be keep improving on it. Just to give you a little bit detail on how we derive this kind of information from spectroscopic observations. What we have actually in this particular study, I'm just taking a case example of this particular study and explaining you what we have done is that we have observed that Mare and Highland in general, if you see that they have different trends. So this when you plot this continuum slope and bend depth, the trend you get from Highland and Mare are actually different. So you have to come up with a certain kind of methodology which can actually accommodate all these changes and not only dependent on a specific. So suppose if you derive a methodology which works for Mare probably will not work on Highland because the responses are different. So that's why you have to come up with a certain way of dealing with this kind of situation in order to apply your methodology on a global scale. So what we have done is we took this kind of, so because we have now global map of moon from Chandrayaan-1 moon mineralogy mapper spectrometer data. What we do is we take fresh crater locations from Mare, from Highland, from Mare Highland boundaries, and from South Pole Aitken Basin, from all possible diverse places, and then we actually try to relate it in the way that we get a parameter which can be actually a sensitive parameter which we have defined in this way. And then when we apply that, what we we get is we apply that and we take LPGRS as a reference. What we get is this kind of global map. And just as a site specific case study I'm showing here is this Mare Serenitatis. So this is a Mare region. What you see from it's in the near site, and what you can see that there are variation from when you compare from this iron and sorry, this legend is somehow missing, but magnesium, calcium, and iron maps. When you see, they give you these maps are not directly correlated to each other, and they give you independent information, which is very important when you do this when you want to map different basalt units. This kind of maps provide you a very good tool. So so these are the different I would say that this is just one case study what we have taken, but there are many systematically advances what we have now seen in planetary exploration. So just in summary, I would like to emphasize that for the upcoming planetary missions, first of all, we have to define a scientific objective, and then we have to develop instrumentation, and with obviously with the constraint of mission and program planning. Instruments on a spacecraft must take measurements that can answer critical scientific questions. So as like we already discussed, that the objective should be very clear, and obviously this instrumentation has to answer these questions, keeping in mind that it should be in mass, time, and energy constraint of a mission. So this kind of missions always have this kind of constraint, and you have to put your instrument with all this constraint, which actually gives you scientific outcome. So this is the main challenge what one has to overcome. And basically we this kind of whatever like scientific objective we keep in mind that require more than one measurement or analytical technique. Thus flight measure instruments must be designed to permit synergy with the other instrument systems. So with this I thank you all.